Right, good afternoon. We seem to have 8 in so far, as usual. Possibly a couple more will join. I think we had 10 steady watchers last time, so it's nearly everyone. Lovely to see you all again, as it were. It's lovely to see that you're there. We're up to 9 now. We'll start in the usual fashion. Today's lesson is called, and I hope that's big enough to see, Types of Generator. So the title is Types of Generator. I'll give you the usual 3 minutes to do the usual jobs, and then we'll make a start. Thank you. I'm also going to talk a little bit over these 3 minutes to provide an answer to a question that was posed last time and the time before by Harry. So Harry, if you're there, or indeed if you're watching this back after, you asked about brushless motors, and I didn't know how they worked. As we've seen in the past couple of lessons, you need brushed contacts to connect to the outside circuit in a motor. Well, I've got something of an answer. Every motor that we've seen up to now has the magnets on the outside, and it has the coil of wire spinning on the inside. Well, in a brushless motor, it's the other way around. So there's a magnet in the middle that spins. The magnet spins, and then you have the coil around the outside. And I think it goes something like this. As the magnet is made to spin, it's done so with an alternating current from the outside. So for half of the turn, the current spinning one way, for the second half of the turn, the current spinning the other way. And so that means that those arms, as they pass through, are always pushed in the right direction. So that's something towards an answer to Harry's question from before. But yeah, brushless motors seem to work by inverting the whole arrangement. The magnet is the thing that spins, the coil is the thing that remains stationary around the outside. And is the beginnings, at least, of an answer to your question. Well, that's 3 minutes. We seem to have a sort of a steady 10 watchers. Really, really nice to see that. Types of generator is the name of today's lesson, but we're going to start in the usual way. We'll start with some questions. And once again, this quiz format just feels like it's working quite well. So a scrap of paper might be useful, or of course you can just do this in your book. I'll do 5 questions on stuff from anywhere within physics, and then 5 questions from the current topic that we're studying. The 11th viewer just joined, could be temporary. Very nice to see you if you are here to join us. Title of the lesson, Types of Generator. We're about to do some recap questions. So question number 1, and these are all fairly short, these. Question number 1, when a spring is stretched, what sort of energy is stored in it? When a spring is stretched, what sort of energy is stored in it? Write these answers rather than commenting them as we did yesterday. When a spring is stretched, what sort of energy is stored in it? Question 2. Which seismic waves cannot travel through liquids? Now, this came up yesterday as well, as it happens, but it is random, this set of questions. Something we studied this year. Which seismic waves cannot travel through liquids? Question 3. The answer that requires a phrase here rather than just a word or two. What is latent heat? Question 3. What is latent heat? I'll give you a moment on that one. So question 3 was what is latent heat? Question 4, what are the units of momentum? Question 4, what are the units of momentum? And question 5, I think, is the hardest one. My prediction is, and I'll have no way of knowing, there are 2 answers to it, and you need them both, but I suspect some will get one of them. I doubt there'll be anyone gets both. We'll see. Question 5 is this. A black body does not something or something any radiation. I'll say that again. There's 2 missing words. Where I've said the word something, you need to replace it with the appropriate word. Here's the sentence again. A black body does not something or something any radiation. A black body does not something or something any radiation. That was question 5. So we'll go through those now. They're all relatively short, simple ones to go through. Question 1 was, when a spring is stretched, what sort of energy is stored in it? The answer is elastic potential energy. Well done if you got it. Elastic potential energy. Question 2, which seismic waves cannot travel through liquids? Secondary waves, or S waves, is the answer. They are the ones that cannot travel through liquids. As we looked at yesterday, that means we know that the outer core of Earth is liquid. Question 3, what is latent heat? This one did require something close to a full sentence. Well, latent heat is the energy that changes the state of a substance. So it could be going from solid to liquid or from liquid to gas, but the energy supplied in that moment of transition. So in water, once it's reached 100 degrees, it needs the latent heat, in that case of vaporization, to change it into a gas. But latent heat, as a general answer, is the energy required to change the state of a substance. Question 4 was, what are the units of momentum? And the answer is kilogram meters per second. kgm/s, you can do it in that shortened form, but it's kilogram meters per second. And question 5, I think, as I say, and I'll be really impressed if you manage to get both of these. Well, it's that a black body does not reflect, and I think some of you will have got that. It doesn't reflect any radiation, nor does it transmit any. Now, what we wrote in our books about that wasn't necessarily helpful. We wrote that black bodies are perfect emitters and absorbers, and they are. They're very good at giving out radiation and absorbing it. What they can't do is reflect any radiation, so any radiation that lands on a perfect black body will not be reflected, but nor can it pass through it, nor can it transmit through it. So the answers were reflect and transmit. Now for 5 questions from this, the most recent topic. So once again, you can number them 1 to 5. Well, question 1 of this list. Where is the strongest field in an electromagnet created by a coil of wire? In other words, a solenoid. Where in a solenoid is the field strongest? Question 2. Which 3 elements are magnetic? Or perhaps put more clearly, which 3 elements can be permanently magnetic? Question 3 is a drawing one. I'd like you to draw the magnetic field that exists between 2 like poles. Draw the magnetic field between 2 like poles. That's a recap of our very first magnetism lesson. It feels like ages ago now. That was actually delivered in school, in your second to last week at school, I think. So draw the magnetic field between two like poles. Question 4, familiar, it keeps popping up. Question 4, what is the definition of a magnetic field? Write that for me, and I'll just give you a moment to write your definition of a magnetic field. Trying to judge that. I was imagining myself write it and then giving a bit more time. I think I've given enough. So question 5, the last question of this recap. An induced current has a magnetic field. In what direction does the induced current act? That's a general question requiring a general answer, and it's to do with last lesson. So when in that second coil of wire an induced current is created, in what direction is it created to act? So that was question 5. We'll go through those, then we'll start with the new stuff. So question 1 of those, where is the strongest field in an electromagnet created by a coil of wire? Or put another way, where is the strongest field in a solenoid? The answer is that it's inside the coil. Just to remind you what I mean by that. If we have a solenoid, then the field we draw around this, and I'm not going to put arrows on this because I'm not specifying what's north and what's south, but the field is like this in the coil. Very close lines like that. Outside of the coil, we have this more spread out field. It moves outwards. But yes, you end up with something like that. So the answer to the question, where is the field strongest when it comes to a solenoid? It's inside the coil itself. You have the strongest field. Question 2 was, which 3 elements are magnetic? The answers were iron, cobalt, and nickel. Iron, cobalt, and nickel. And as we mentioned before, steel counts, but that's only because steel is an alloy of iron. So they all count. Draw the magnetic field between 2 like poles. Again, I'll just show it by drawing it. Field between 2 like poles. So let's put 2 like poles in first. I'll choose, in this case, 2 souths. So there's a south pole, there's another south pole. Well, they in no way wish to interact in terms of their field, and that's reflected in the shape of the diagram that you get. So we can imagine this looping round, but I'm not going to draw that detail in. Do the same on both sides, and all we need to do now is add arrows. So that's the shape of the field between 2 like poles. And then in this case, remember, fields are defined as being from north to south. North doesn't appear on these diagrams, but so a diagram, something like that is what I was hoping for. Well done if you got it. Question 4. What's the definition of a magnetic field? I hope you're almost getting bored of this one because you've had to answer it so many times. It is the region around a magnet where another magnetized material or magnetic material experiences a force. The region around a magnet where another magnetic material experiences a force. Question 5, an induced current has, we have to answer generally. It will act in a direction, and this was the phrase from yesterday, to oppose the change that created it. It acts in a direction to oppose the change that created it. And we saw that both on the diagrams we saw on the board and in the notes that we made, that the induced current and the induced field due to that current, they act in a direction to oppose the change that created them. So that's some recap of some older stuff and some very recent stuff. Well, we're going to pick up with this idea of electromagnetic induction, of the generator effect. And the first thing, I've not got as much to show you live today. I have one demonstration. I'm going to be using the board a little bit more. And the first thing I'd like to show you is actually something you first saw, well, I guess nearly 2 years ago with me. 2 years ago, we were doing about the topic of energy, which is your very first GCSE physics topic, the very first thing I taught you. Well, that topic ended by looking at renewable and non-renewable energy resources. And I put up this picture of how power stations work. I'm just going to zoom into it now so I can talk through it once again. So I think fairly big and prominent on your screen is this picture of a power station. I think it's clear enough from what I can see on the screen I'm looking at it from. I think you can see the letters nice and clearly too. I'm going to refer to some parts of this diagram by the letters. So last year, we didn't pay much attention to the part labelled A. That's called a generator. And I just described it really as some sort of magic thing that you make it move and electricity can come out of it. Well, based on what we saw last time, we now know a little bit more, but let's take the story backwards, just as a recap if nothing else. In a traditional thermal power station, and this doesn't have to use non-renewables, but traditionally it would. At part D, you'd see coal, oil, or gas being shoveled in some way to a furnace. C is the furnace, D is the raw fuel. So let's imagine it's coal. Coal is fed into this furnace, part C, and it's burned. Then we have this pipe work. So you have water coming in, but once that pipe full of water goes into the furnace, it gets so hot that that water turns to steam. So far we have that coal is burned, and then that heat turns water to steam. And that steam is then fed through a turbine. Part B is a turbine. So that steam makes a turbine spin. And that turbine is connected to the generator, so the generator spins too. And as I say, last year, that's where we ended the story. We just said, generator spins, electricity is created. Well, now we know more. Now we know a little bit about magnetism and about electromagnetic induction, the generator effect. We know exactly what's going on in that generator. We know that a magnet's spinning, or maybe a coil is spinning, something is spinning inside a magnetic field, and that is how the generator works. So you use the steam to make the spinning happen, you use the coal and then the steam to make the spinning happen. But yes, inside that generator, there is some sort of spinning magnet or spinning coil of wire generating electricity. So we've kind of unlocked the secret of this part A of the generator. And that's how power stations work. They work on a huge scale, but I'm going to show you now for real a very small version of what I've just described. So again, I'm just moving the camera around. I'm going to show you my only demonstration of today. Some of the equipment today familiar. We're using this micro voltmeter again, which you're about to see. And this is on a very simple, this is a micro voltmeter, and the reason I'm using a micro voltmeter is I need it to be sensitive. It needs to be sensitive enough to the small amounts of electricity that I'm going to make. I'm just going to bring in everything nice and tight, or as tight as I can, so that you can see really clearly what's going on. Right, clear enough, I think. My first job is to make it go back to 0 so that we can see in what direction the electricity is being generated, the potential difference, the voltage is being generated. Anything to the right we'll call positive, anything to the left we'll call negative. And all I've got is a coil of wire. I'm just doing that to improve the size of the effect. You saw that in evidence yesterday, that the more wire we can get into the magnetic field, the bigger the generator effect will be. So I've just used sellotape to coil a big long loop of wire, and I've put both ends in. So once again, we're starting with a lot of very similar raw materials. We need a coil of wire, a conductor. And this is my magnet. And it's just mounted so that I can make it spin. And so you'll see, hopefully, as I spin it, you'll see this needle move. And that will show that electricity is being generated. So I'm just going to hold the coil in front of the spinning magnet. I'm going to get it as close as I can to hopefully make the effect as big as possible. In fact, I'm just squashing it such that it can more or less fit inside it. And now as I spin it, even if I spin it quite slowly, you can see a wobbling on that dial. If I spin it really fast, you actually don't get as much of an effect. Now that's misleading, actually. The faster you spin it, the more voltage you get. Just this needle has a bit of delay to it. You can see there's a bit of a lag. It has to go and then move around, and as it does so, it can't keep up if I spin too fast, and it just hovers around the middle. But if I do it a bit more slowly, you can see the effect. We're generating alternating current. You might remember that phrase from when we did electricity last year. Alternating current, or AC, is current that first goes one way, then the other. So inside this wire, we can imagine it's looping around clockwise, then it's looping around anti-clockwise. On this dial, we see that as it going back and forth. But this is what's happening on a very large scale inside a power station. You have huge coils of wire, and crucially, you have huge magnets. And they rotate inside the coils of wire, and they generate electricity. Just watch even more closely now. So it's slightly unbalanced, this magnet. I'm going to do a half turn, and I want you to see it goes one way, and then the second half of the turn, and it will go the other way. So in this first half turn, it deflected left. In this second half turn, it should deflect right. I'll do that again. So first half turn, deflect left. Second half turn, deflect right. So in a full cycle, it deflects one way, then the other. You have alternating current. Well, in a real power station, the magnet much bigger. I'm given to believe, not that I've ever seen one, they're about the size of a double-decker bus, the magnets that are used. And they are made to spin 50 times per second. So they do one full rotation 50 times in a second. And that is the electricity that is now powering everything you're seeing here. All the lights that may be on in your house, all the devices are powered by huge magnets in power stations spinning 50 times per second, making AC, alternating current. So what we're going to learn today is the two different types of generator that you can get. This thing here, to be clear, this is a generator. And depending on how you wire it all up, you can either use it to generate AC, like this is doing, one way then the other, or you can use it to make DC, where the current all goes one way at the same time. Now, before we make any notes on that, and there aren't substantial notes to make today, the diagrams I've given you are more or less all the notes we're going to make. I'm just going to show on my screen two pictures of these two different sorts of generator so that I can talk through them first. So I'm just moving the camera around once again, just bear with me. And I'll zoom into that so you can see it as clearly as possible. I've lost something, which is why I'm pausing for a minute. Right in front of me, always. Right, so at this point in the lesson, I hope you understand a little bit more what's going on inside that generator. Spinning magnet surrounded by a coil of wire, generating an alternating current. As the field lines cut through the coil in one direction, you get a current induced in one direction. As the field lines in the second half of the turn cut through in the opposite direction, you get an alternating current. Sorry, you get a current induced in the opposite direction. Well, The difference between the two generators, and we'll look at it more carefully in our diagrams, is purely on how they're connected here. So you'll see this is a DC generator. Sometimes they're called dynamos. And that's why I've written the word dynamo there. But this is just generating electricity, generating current, always in the same direction. I think you can pick out on your screens, there's an ammeter pictured here. And you can see that that ammeter has 0 in the middle and is always generating current in one direction. It's not making a constant amount of current, and that's also shown by this diagram here, that you get this sort of half wave. So it's always above the 0 line. So the current is always in a positive direction. It's always going, let's say, clockwise. Doesn't change the direction it's flowing. But the speed of the flow does increase and decrease as this rotates through its cycle. But it's kept in the same direction because it has one of these things again. And remember this phrase from a couple of lessons ago, it has a split ring commutator. So it disconnects and reconnects every half turn. And what that allows it to do is make sure that the current is always being pushed in the same direction. What's never clear from this is how this is spinning in the first place. So do remember that we've got to imagine this is all connected to a turbine or something. So maybe here, this little thing here runs off to a turbine that's spinning. The spinning comes from the outside on one of these. Remember, you have to have some energy source, whether it's burning coal, whether it's something else. You have to have something making this arm spin. But when you make this arm spin, you can generate electricity because it's inside a magnet. So that one's called a dynamo or a DC generator. And you'll notice, again, keep forgetting to change the name. This is not Fleming's left-hand rule, ignore that. This is an AC generator. And you'll see that it's basically the same. It's got a magnet still stationary around the outside. It's got this loop of wire inside the two poles of the magnet. The only difference is the way this connects up. This connects up with two separate rings, rather than one split ring commutator, two separate rings. So this circuit never disconnects. This circuit remains constantly connected. And what that means is that the current, and you can see it from the little electrons doing a dance, the current either flows one way or the other, depending on what half turn that coil is on. So you get AC out of one of these. So the first one I showed you was a DC generator. And because it has a split ring commutator, it disconnects and reconnects every half turn. And that means that you always get the induced current in the same direction. Whereas this one here is an alternator or an AC generator. And so because this is constantly connected, it has two separate rings connecting it. That means that you get this alternating current. The current will flow one way and then the other. Well, we're going to take some notes now, but as I say, actually, there's barely anything to add to the things I've given you before you do some work. So this is a lesson that I think will come out more or less bang on time. Let me just adjust the camera and then we'll do some work. I'm just seeing if any questions have come through. Two very good questions, I think. So I'm going to pause and take now. I'm just going to adjust my camera so I can answer them directly. I'll take some questions and we'll do some notes. If any of the rest of you have any questions, now is the time to ask a few as well. Right, so if I've understood how the YouTube comments work, then I think you can all see the questions that come up, which is one of the really nice things about it. So Max asked, do magnets ever lose their magnetic fields? And the answer is yes, they can do. This is a really good example, actually. I'm going to bring it close to the screen. So this is the magnet I had before. It's a horseshoe magnet. And this thing here that's attached to it is called a keeper. It's just a piece of metal. And actually, it's a really strong magnet, so it's a bit tough to remove and a bit scary when you put it back on. You nearly always get your fingers trapped on it. But I'll sacrifice myself for science here. The answer to your question is that yes, they do lose magnetism over time. I did briefly, and this was back when we were at school, mention what causes magnetism, and I was very vague about it. This idea that the way the electrons line themselves creates these things called domains inside a magnet. Now, in a normal piece of iron, the domains are in a random direction, but inside a magnet, the domains have been all made to line up in the same direction, and you get a magnetic field. Well, over time, those domains can sort of move out of shape, stop being aligned, and so this can become weaker. And I showed you the quickest way to do that is with a hammer. If you take a hammer to any permanent magnet, you will sort of disrupt the direction of all its domains, and it will become less magnetized. But it happens less spectacularly over time as well. Adding a keeper to a magnet when you're not using it, like this. Watch for my track fingers. Oh, terrifying. There we go. Adding a keeper to a magnet is just one way that you maintain its magnetism. So as far as I know, this is many, many decades old from our school science department, and it's still a really strong magnet. But they do lose their magnetism over time. And James asked a question too. Oh no, he answered the question. And yes, I should always read ahead because someone has already answered the question really well, as James has. But I hope I've added some detail. Yeah, they do lose their magnetism, but they lose it very slowly. Right, we'll do, as I say, barely call these notes. I'm going to talk you through the printout I gave you. So I'm going to adjust the camera and you just grab the printouts. This is the one that had pictures of our two different types of generator on it. And I will just adjust my camera. Right. And this is a landscape sort of scenario, so I'm just moving this box that I put things on. Very little to add then, as I say. This is more about me talking through what you're seeing on these. So that's the handout that I'm talking about. And we'll deal with the direct current first, perhaps. Just grabbing my pen so I can add some things to it. This piece of paper, I'm essentially imagining that in the end you'll fold and just stick in, and I'll give you a moment to do that in a moment. But what they show is the two types of generator side by side. I'll just try and make sure that you're seeing what I'm seeing there. The two types of generator side by side. And as I say, they are almost identical. You can see the only difference is the way that they connect up. If you're wanting to create a DC current, a current that always flows in the same direction, use a split ring commutator. However, if you want to make an AC current, one that does go in one direction and then the other, you use these, they're called slip rings, these two full circles of some conducting material. My guess is they're often made of something like copper, but you make these slip rings, and that way of connecting it up ensures that you get AC current out. Well, that is more or less all there is to it. Now, what I've put above is just pictures of the level of induced voltage you get. So what this is showing is when it's vertical, you start at 0 volts. Then as it cuts through the field, you get maximum when it's horizontal, cutting through the field. Then it goes vertical again, goes down to 0. That's the moment when the two arms are sort of parallel with the lines of the field. What I mean by that is here. You can see when these are vertical, these arms are vertical, they're kind of lining up with the field, not through these lines, but going along them, not cutting through them. Then as it rotates again and it's on its way back up, it's cutting through field lines again, and you induce quite a lot more current, down to a minimum. So you're going through a cycle of maximum voltage produced and minimum voltage produced. But what you need to note for this one is that the voltage is always in the same direction. It doesn't dip below 0. And that's in contrast to what you see here. It does the same thing. It makes maximums when it's cutting through these field lines shown on the diagram. When it's cutting through those lines of flux, you get maximums. You get minimums when it's kind of running parallel, just for that moment, running parallel to the lines of flux. But because of the way this one's connected, in half the turn, it's inducing a voltage in one direction, and therefore a current in one direction. And in the other half turn, it's inducing a voltage in the opposite direction. I think all I wish to add to these And you can, at your own leisure, have a good look at these and check it all makes sense, and ask any questions you need to, either now or later. The only thing I want to add is next to direct current, let's just write dynamo. Sometimes it is known as a dynamo. And next to where I put alternating current, or rather below it, where I put alternating current, this is sometimes just called an alternator. But what they are both is they are both generators. And perhaps the other thing I just want to draw attention to is this rotation, because what these pictures don't show is where that rotation comes from. So remember, it depends on the machine, but that rotation in a power station comes from the turbine spinning. So I think what I wish to add, and if you don't like the way I've laid this out, you can look at it and change it. But just drawing attention to this axis of rotation, I just want this idea that the rotation is provided by an external force. That force could come from the burning of coal. That force could just be someone moving it by hand, but something external has to provide that rotation. So we'll just put rotation provided by external force. The camera, then it's going to be over to you to do a short bit of work, and then we'll go through it. So stick that in if you can. Thank you. On my trusty timer, and I choose a time limit. The questions are the ones I sent to you, a little bit shorter than yesterday's. I think 10 minutes, because there's a lot of short answers to it. 10 minutes might be appropriate, but given that we're not too time pushed, I'll give you 12 actually. So I'll give you 12 minutes, and in those 12 minutes, I'd just like you to try and answer these questions. It starts with a picture that's hopefully familiar to you now of an AC generator, an alternator. So see if you can make sense of these questions, and we'll go through them, and that is today's lesson. 12 minutes on the clock now. And see how you do. Thank you very much. I'll keep an eye on the comments as always. Good question, Max, and yes, you've perceived that correctly. And it's why I love this topic, because it sort of suddenly you start to understand how lots of things must work. And absolutely, in the case of a wind turbine, it's just that the power of the wind provides the force that makes those arms spin. And so inside the box at the back of that wind turbine, there'll just be a magnet spinning. And as soon as you make a magnet spin, you can generate electricity. That is the power of the generator effect. Same for hydroelectric, that there'll just be a dam across a river, and there'll be gates in that dam that can be opened, and inside those openings there'll be a turbine that can spin. And again, the turbine will make a magnet spin and you generate electricity. But as you see in the question following, it's how wind gauges work. You might have got to that, you might have not. Even, I'm not sure this is how they work, but you can even begin to imagine how car speedometers could work. All you need to do is attach a magnet to the moving wheel, and that will generate an amount of electricity proportional to the speed that that wheel is spinning. And then you can just have a needle as part of the circuit, and you can create a speedometer. So you begin to see how loads of things must work once you understand electromagnetic induction. Just under 5 minutes left. one more minute, then we go through this. Just let me know now if you feel like you need a lot more time. Just tell me by the comments, but if not, we'll go through this in a minute. Hope that was enough time. I've certainly not heard anything to the contrary. So we'll go through this, and that will be our lesson. And we should come out more or less on time, which is good. It's hard to do in these lessons. But let me just adjust the camera. Right, I think everything in view that needs to be, and clearly you can refer to your copy if it's a bit blurry on the screen. But question 1 said, the diagram shows an AC generator. The coil rotates about the axis shown and cuts through the magnetic field produced by the magnets. Well, A part I starts like this, induced between X and Y. Use the correct. The effect is caused by the, if you got that. What do the letters AC stand for? I've mentioned it today. If not, you're having to delve back to last year. But AC stands for alternating current. Name an instrument that could be used to measure the potential difference between X and Y. That question is testing a few things, not least it's testing, do you know what potential difference is? So the name, of course, is voltage, and if you know that, this becomes easier. The instrument you could use is a voltmeter. Spelling probably doesn't matter on a question like that, but just note that even though we in Britain spell the word meter as in a measurement of distance, M-E-T-R-E, a voltmeter is spelled volt, V-O-L-T, M-E-T-E-R. It's what we'd call an Americanized spelling, but actually that's true of any measuring device. So an ammeter is the same, A-M-M-E-T-E-R. It always ends E-R, not R-E. Part B started like this. Graph 1 shows the output from the AC generator, and we're shown this wave pattern. Part I says this: one of the axes on graph 1 has been labelled potential difference. What should the other axis be labelled? Well, the other axis measures time. And again, well done if you got that. Part I says the direction of the magnetic field is reversed. So they just swap the poles of the magnet around. On graph 1, draw the output from the AC generator if everything else remains the same. So it's worth 2 marks, and you have to always take a bit of time to get this right. If the poles have been reversed, then clearly the direction will be opposite. So we're going to draw something that is sort of the mirror image of this, but get the details right. So make sure that it goes to the same peak. So what you're seeing here is me just marking the height of the peak where I'll be labeling it. And again, obviously we're doing this roughly. But yeah, taking a bit of time to get this right is no bad thing. So I've now marked the peaks and the troughs of this wave. The wave to draw in anyway is sort of the mirror image. So something like that would do nicely. I'll be honest, I'm pretty pleased with that, done by freehand and a felt tip. But yeah, something like that, that mirrors the original wave, is what you would get. Now part C says this, the number of turns on the wire is, the number of turns of the wire on the coil is increased. This increases the maximum induced potential difference. State two other ways in which the maximum induced potential difference could be increased. So they have mentioned number of coils. Well, we could increase the strength of the magnet. So increase magnet strength. The other one that occurs to me is about increasing the speed of rotation. There may be others, and if I've forgotten something, you can comment and I can tell you if that would be appropriate. But this idea that you can increase speed of rotation. That would also increase the output, the maximum output voltage. I'm not seeing any questions pop up. Again, I might be moving too quick, but they're the ones that occurred to me, and well done if you got them. That question was out of 8. You can put a mark out of 8 for that one. And we'll move on to the second and final question. And on this one, yeah, I think I really like this topic. I was saying this while you were doing the work in answer to Max's question. I really like that suddenly you understand how a device like that, which could be a mystery to you, suddenly you understand how it must work. A wind gauge is made, and this is a simple DIY one that uses plastic cups and a spindle and some sort of support. But the heart of the device is a spinning magnet and a coil of wire, because we now know that's all you need to generate electricity. Well, A goes like this. Explain why the wind caused the AC voltmeter to give a reading. The explanation has been started for you. So we're told the wind causes the plastic cups to turn. Well, let's link that then to the magnet, because it is linked to the magnet. I think that gets one of, we're looking for 3 marks here. Now we need to go from the magnet to the coil in some way. And remember, there was a useful phrase last time. I think a really good way to answer this is about how the field lines will cut through the coil, or vice versa. But I'm going to put it like that, that the field lines cut across the coil. And then we need to say the result of that, where a magnetic field cuts across a coil of wire, it will induce, and let's be careful how we say this. I'm not going to say it will induce a current, because this picture has a voltmeter, and we're being asked to explain why the voltmeter has a reading. So I'm going to put that a potential difference is induced. You could use the word voltage too, but a potential difference is induced. That's how you get 3 marks there, I feel. And then part B, the final part, the gauge is not sensitive enough to measure light winds. Suggests one way that the design could be modified to make the gauge more sensitive. Clearly there's some choice here. I'm going to put use stronger magnet. You may have gone for the other, what I think is the other obvious one, which is that you could use more coils. They're the 2 most simple changes you can make to make that gauge more sensitive. Stronger magnet or more coils will increase the size of the generator effect for a given wind speed. Right. You can give yourself a mark out of 4 for that, and then a total mark out of 12 if you like to keep account of such things. I'll do some final remarks and then I'll let you get on with the rest of your day. I'll tell you about next week as well. So let me just adjust the camera and say my goodbyes. Right, well, thank you for sticking with that. And I hope it's now clear how generators work, both AC generators and DC generators. They work the same is the answer. It's all about the connection, whether they use a split ring commutator or whether they use those two separate slip rings. And from that, you either get DC or you get AC as the outcome. In terms of next week, we'll carry on as normal. So that will mean we have a lesson at 2:10 on Thursday, because we always do, but a lesson quite early in the morning on the Friday. I can't remember if that's week A or week B, I've lost track at this stage, but it will be at 9:10 on the Friday. And what we have to cover, we're still going to need about 4 lessons, I feel, to cover the entire topic. And so we won't be finished next week, but there are, I think, some really interesting lessons coming up. One task I now have between now and Thursday work, we'll see how that goes. So I'm going to show you how loudspeakers work, how microphones work, and as part of that, I may even have to sing. Don't get too excited. I may have to sing. I may hold back on that because I think if you hear the velvety beauty of my voice, it will ruin music forever for anything else you choose to listen to. So you may even see me play my trumpet instead. Speakers work. That may or may not all be in one lesson. And the last thing we've not learned about, and it takes 2 or 3 lessons to learn about them, is something called a transformer, a massively useful device in our lives. So every time you plug your phone in to charge it, a transformer steps down the voltage to make it safe. We use transformers in our power lines. Most devices you plug in, a computer, another for example, use transformers. And we're going to learn how transformers use this generator effect to their advantage, to be able to step up and to step down voltage. So quite a lot still to learn. For now then, as always, stay safe, enjoy the rest of your day, and just look out for your emails probably midweek next week. I'll probably send out the email the day before, as I tend to. So on Wednesday, look out for your emails because I'll be sending materials to help us learn about loudspeakers and about microphones. For now then, goodbye. Thank you for tuning in once again.